Okay, so we're back with chapter 7. We're going to do 3 problems from here. Again, you should write the problems down. You should actually see if you can do the problems on your own and then come back and check it with here. Keep it in mind, of course, there could be different ways to prove the problem. All right, so here we have example 10. And again, I'm looking at the 9th edition. So double check the numbering may be off, but the problem should be in your book. Okay, I did check to make sure the problem's in your book, but the numbering might be off. All right, so let A and B belong to a group. Okay, so chapter 7, we're talking about cosets and Lagrange theorem, just a FYI. So cosets and Lagrange. All right, so let A and B belong to a group. H and K are subgroups of G. If AH equals BK, prove that H equals K. Okay. So again, starting off this proof, just general information. Let A, B belong to this group G. I'll assume with H and K being subgroups of G. And suppose AH equals BK. Okay. Show what? We have to show that H equals K. Now, here I know you might be thinking of, showing that they're subsets of each other, but because we're in this chapter, you want to look towards the properties that we have. So always sort of go to the properties first to see if there's some type of maybe shortcuts or things you can use, properties you can use to help prove things. Okay. One of the things that we have, since we're supposing AH equals BK, right, where H and K are subgroups, then from here we can say that if we take B inverse on both sides, we can say that B inverse AH equals K, right? We can do that, okay? Again, knowing that A and B is in G, which is a group, so we know B inverse is this, so we can take B inverse on both sides. And since we also know that K is a subgroup of G, then B inverse AH is a subgroup of G, right? And that's just because it's equal to K. And if K is a subgroup and if it's equal to K, then that has to also be a subgroup, okay? Well, now we can use something from a property that we have dealing with cosets. By property 9 in the lemma on cosets, that tells us that B inverse A belongs to H. Okay, so go back and verify that property to make sure you understand and agree with that property. Okay. Well, hence, we know if B inverse A belongs to H, then by the first property, either the first or the second property, we can say then that B inverse AH equals H, right? Because if you belong in that H is a subgroup. So if you belong in H already, when you take an element and compose it with H, it's going to remain in H. It's going to equal H, right? Okay. Which is equal to K. And we are done with this proof. Not bad, right? Okay, let's move on. Okay, so our next proof or problem, which is a proof. Let G be a group with the order of G equal PQ, where P and Q are prime. Prove that every proper subgroup of G is cyclic. Okay, so again, just starting off with our basic information. Let G be a group with order PQ, where P and Q are prime. Okay, let H be a proper subgroup of G. Okay. And our goal is to prove that H is cyclic. Okay, that every proper subgroup of G is cyclic. Okay, and if H is any general proper subgroup, then once we prove it for H, we've proved it for all the proper subgroups. Okay. Well, we know, so by Lagrange theorem, the order of H divides the order of G. And we can say since H is a proper subgroup, of G, then the order of H is either 1 or P or Q, right? Okay. Well, if the order of H equals 1, then that tells us what? That H is equal, is just identity, which is clearly cyclic. Okay. Also, if the order of H equals P or Q, all right, and PQ can't be included because this is the proper, right? And I think I said that, but just want to make sure we're good on why PQ isn't considered as one of the orders of H. It's because we're looking at proper subgroups. If the order of H equals P or Q, then by corollary 3, it's cyclic. We are done with this problem. If you're doing this in general, you can just say by corollary, by theorem, as long as it's clear that I know and it's clear that you've set up enough information to use the theorem or the corollary, then that's fine. Okay, let's look at one more problem. Okay, so our last problem is a computational one, and we are going to compute these values. Of course, we're going to use our shortcut way to help us, and that is, for this case, using Fermat's theorem. So let's look at, so by Fermat's theorem, and I guess you could also think about using Euler's theorem as well, right? But Euler is a specialized form of Fermat's. So we really are using Euler because it's a specialized form of it. So by Fermat's theorem, A, we know that 5 to the 7th is congruent to 5 mod 7. Okay, so how will that help us? Well, we can take 5 to the 15th and rewrite it as 5 to the 14th times 5, right? Because you want to rewrite it in multiples of 7. All right, so you can use the fact that 5 to the 7th is congruent to 5 mod 7, right? Well, this is equal to 5 to the 7th squared times 5. This is congruent to 5 squared times 5, which is equal to 25 times 5, which is, now if you want, you could just do 125, or if you want to simplify that 25 in mod 7, you can say, well, that's congruent to 4 times 5, right, in mod 7, because 25 is congruent to 4 mod 5. And then that equals 20, which is congruent to 6 mod 7. And so our answer is 6 mod 7. Okay. Pretty fun. This is, if you have a chance, if number theory is being offered while you have a chance, this is a lot of what we do in number theory, which is a really interesting and cool course to take. Just playing around with whole numbers, primes, and different theorems and things, which has now been used in applications for a long time. It was just used in pure math to just kind of enjoy mathematics, but now they're applying some of those principles in number theory to do code breaking and things of that nature. Okay, 7 to the 11th is congruent to 7 mod 11. Right, 7 to the 13th, we can rewrite as 7 to the 11th times 7 squared. And so that's going to be congruent to 7 times 49. which is congruent to 7 times 5. And we're mod 11, which is equal to 35, which is congruent to 2 mod 11. So our answer is 2. All right, we are done. Hopefully you understand these problems and just continue practicing in preparation for the exam. And I will see you all in class.